Good morning and welcome to lecture 55. Today's lecture we will be covering a detailed discussion on MIMO capacity. A part of this was begun in the previous lecture, and today's goal would be to complete that discussion and also to provide a brief introduction to the use of coding along with the multiple transmit and receive antennas. So let us, the framework is the MIMO framework that we have been looking at the past few lectures. We have a set of NT transmit antennas, at the receiver we have NR receive antennas, and we have a rich Rayleigh scattering environment, and this gives us a MIMO framework which is given by the following equation, where you have the receive vector is equal to H times X plus noise and the different dimensions NT cross 1, this is NR cross 1, NR receive vector NR cross NT, X has got a NT cross 1, NT transmit antennas, and the noise vector is 1 per receive antenna, which will be again NR cross 1. Given this framework, we are now trying to look at the case of capacity in the context of a system where the transmitter does not have knowledge of the receiver, because in the case where the transmitter has knowledge about the channel, then we can do the singular value decomposition of the channel, which then creates the eigen decomposition and then the parallel channel transmissions that we can do by using pre-coding at the transmitter and then followed by the post-processing at the receiver. Now, in the case when there is no knowledge of the channel at the transmitter, we are looking at it more in the form of the ergodic capacity. For that, we would like to look at the definition of entropy, and the entropy is defined or the mutual information is defined in terms of H of y minus H of y given x. So that is the form that we are going to be working with, and we would like to derive the results based on that. Okay. So now we did two cases in the last lecture. I would just like to refresh your memory, and using that we will build on today's lecture. The first of the results was for the case of a scalar complex Gaussian, using the PDF and using the understanding that the expression for the entropy is given by minus expected value of logarithm base 2 of the PDF. Using that expression for a scalar complex Gaussian, we got the expression to be logarithm base 2 pi e sigma squared. Sigma squared is the variance of the Gaussian random variable. Then moving on from the scalar to the vector case, the entropy of the vector source is given by logarithm base 2 pi e times r, determinant of pi e times r. So with this as the framework, we would now like to continue our discussion and build on that. So this form can also be written in the following way. This can also be written as logarithm base 2, bringing out the pi and the e pi power n determinant of r. So given this expression where r n is the dimension, n cross n is the dimension of r. So this form is also useful for us sometimes in our discussion. So given this framework, now let us quickly get the key observations and results. The mutual information between the input and the output, I of x vector x and vector y. This is given by the entropy of the vector y minus entropy of y given x. Again, these are basically a repetition of what we had discussed in the last class. This is given by h of y minus the entropy of the noise vector. And we showed a couple of results. Let me just mention those. The dimensions of h are NR cross NT, that is the MIMO channel representation. and we are interested in the autocorrelation of the vector y, that is given by H times Rx times H Hermitian plus Rn. This was the result that we had obtained in the last lecture. For dimensionality, this would be Nr cross Nr, again this would be Nr cross Nr, and Ry would also be Nr cross Nr. So, this is the expression for Ry. Substituting this in the expression for the entropy, we can now write down an expression for the capacity. So, the capacity expression, that is mutual information between x and y, vectors x, can be given as expected value of logarithm base 2 pi power nr, that being the dimension, e power nr determinant of the following matrix, H times Rx H Hermitian plus Rn. This is the first determinant for the logarithm. The brackets are as follows, and expected value would be minus expected value of logarithm base 2 of or maybe I just keep the expected value outside, minus logarithm base 2 of pi power nr e power nr determinant of Rn, and the outer bracket for the expectation. So, this is the obtained directly from this result, writing the expressions for the entropy using the form given in the previous slide. So, now simplifying this, the capacity or normalized capacity C by B given by the mutual information is nothing but expected value of logarithm base 2 of there is a difference of logarithms. So, this is a ratio of these two. It is determinant of H Rx H Hermitian plus Rn divided by determinant of Rn, and that is the expression within the for the logarithm, and then the expected value of the entire expression. So, this is the form that we will start to work with. Again, this is a very useful result, a very powerful result that we now have. Now, if we go back and make the Gaussian assumption about the input. So, if we assume that the input is a Gaussian source where the vector components are independent, then we can write down the following value. So, that is x is a nr cross 1 x nt cross 1. So, nt transmit antennas are there, it is an nt cross 1 complex Gaussian vector, complex Gaussian zero mean vector with and the values are it is in the form of an and the values are independent of each other, the components, independent complex Gaussian zero mean. So, in that case, the autocorrelation matrix Rx given by expected value of x Hermitian can be written as the variance of the Gaussian random variables sigma x squared times the identity matrix, and the dimensions of the identity matrix would be nt, because it is an nt cross 1 vector. So, this is the expression for the Rx. Now, using this value in 1, using 2 in 1, using the result for the Gaussian vector in the expression for 1, we now get a very powerful result which says that the normalized capacity is given by expected value of logarithm base 2. Basically, I am going to write determinant of Rn, 1 over determinant of Rn, as I am going to write it as the determinant of Rn inverse. So, if you write that write it in that form, we get logarithm base 2 of the determinant of the following expression: h times Rx times h Hermitian plus Rn times Rn inverse. This is the expression that we have. Then we have the brackets for the logarithm and then the expectation value. And basically simplifying this expression, we also note that we can use the expression for Rn as sigma n squared, that is the variance of the noise. It is an nr cross 1 vector, each of them are independent Gaussian variables. So, this would be I times nr. So, now substituting, if you call this as equation 3 and 4, substituting equation 4 in 3, okay, substituting 4 in 3, then we get the following expression. We get the following expression that C by B can be written as expected value of logarithm base 2 of determinant sigma x squared by sigma n squared h Hermitian plus I n r, and this is the brackets for the determinant, the brackets for the logarithm, and then the expected value. Okay, so this is the expression that we have, and this is what is often referred to as the log dead capacity of a MIMO channel. We have the logarithm of the determinant of an expression, and this is called the log dead capacity of a MIMO system, MIMO channel. Okay, now there are several very interesting results that we can derive from here and build on and get a good understanding of the characterization of the MIMO channels. So, the just to summarize, we are making the assumption that the channel is not known at the transmitter. Channel is not known to the transmitter, because if it were known, then the best thing to do would be to do the singular value decomposition, and then followed by the water filling for the optimum power allocation. So, channel is not known at the transmitter. So, therefore, we have resorted to estimating the ergodic capacity. Now, we have also in the deriving this expression, we have made the following assumption, that the input to the channel is a Gaussian. Input to channel is the source has Gaussian distribution. So, it is assumed, that is x of n, the vector x is assumed to be Gaussian. Under that assumption, we have simplified the expressions that we have given. And third assumption is that the dimensions of H are nr cross nt. So, which basically means that the dimensions of H Hermitian will be nr cross nr. Okay. Now, if H is full rank, if H is full rank and we have nr is less than or equal to nt, then the rank of H Hermitian, its full rank H Hermitian will be also NR. So, in the case where NR is less than or equal to NT, the case where the number of receive antennas is less than or equal to the transmit antennas, H Hermitian has got the dimensionality that is consistent with the rank of H. On the other hand, if you were to look at H Hermitian times H, this would have dimensions NT cross NT, right. H has got NR cross NT, for H Hermitian would be NT cross NR, and this. So, and in the case where NR is less than or equal to NT, we will find that H Hermitian is rank deficient, because it has a dimension NT, whereas the dimension, the rank that is of the matrix H is only NR, and therefore this would be rank deficient. So, keep this point in mind, because this will come back to help us in the subsequent discussions. Okay. So, now let us take this discussion a little bit forward by looking at the properties of H Hermitian. Properties of the H Hermitian. So, the first observation is that the dimensions of H Hermitian dimension are NR cross NR, because H has got dimension NR cross NT, H Hermitian would be NR cross NR. The second observation, a very important one, is that H Hermitian is by nature Hermitian, by virtue of its structure. If you take Hermitian of it, you get back the same expression. And more importantly, the third property is what is most important. H Hermitian is positive semi-definite, is positive and semi-definite. Okay, the definition of a positive semi-definite matrix is known to you, so therefore I will not write it down, but basically when you have this form, it means that the eigenvalues lambda I are all real valued. Positive semi-definite means they are all real valued, and because and they are also greater than or equal to 0. These two are the properties are reflected by a positive semi-definite matrix. Now, we can also, using the same reasoning as we used to show the positive semi-definite property of H Hermitian, we can also say that H Hermitian H is also positive semi-definite. Positive semi-definite. Again, these are useful properties when we go into the analysis. So, another important observation which is helpful for us to note is that if lambda I is equal to 1 through L are the non-zero eigenvalues, are the non-zero eigenvalues of H Hermitian. Okay. Now, what does this mean? If the rank of H is L, then H Hermitian will have a set of non-zero eigenvalues, and these are the non-zero eigenvalues. We can show that this set are also the non-zero eigenvalues, of H Hermitian H. Okay, so there are some very interesting structures that are properties that are present between H Hermitian and H Hermitian of H Hermitian times H. Now, where does this come into play? In the following property, which I believe is a very useful one for us to interpret the log dead capacity. Now, if you were to look at the expression determinant of some positive constant alpha times H Hermitian, So, this is a positive real scalar, real valued scalar. Okay. Alpha times H Hermitian, and H Hermitian has got dimensions nr cross nr times plus I of nr, identity matrix of nr. So, basically we would like to understand what this what is the property of this, because this this identical expression appears in the log dead capacity if you were to look at the previous slide. So, I will call this as equation 1. I am going to sort of build on this and draw some insights. The first step is to look at the singular value decomposition of H. Now, again we are looking at the case where the channel is not known at the transmitter. So, we are trying to understand the property of this expression, not necessarily trying to do pre-coding at the transmitter. So, if you were to do the following property, U sigma times V Hermitian, that is the singular value decomposition that we have seen before, then we can say that H Hermitian, if you substitute, will be of the form U times sigma squared times U Hermitian. And we also know from the property of the unitary matrices that U times U Hermitian, U times U Hermitian is the identity matrix, and that will have the dimensions of nr cross nr. So, if I call this as equation 2 and equation 3, then if I substitute 2 and 3 in 1, so substituting 2 and 3 in 1, we get the following expression, that the determinant of alpha H Hermitian plus INR can be written in the following form, that it can be written as determinant of alpha U sigma squared U Hermitian plus U Hermitian. This is the form that we would do. Then of course, simplifying the expressions that we have, this is nothing but determinant of U within the bracket alpha times sigma squared plus INR times U Hermitian. So, basically we have a multiplication of 3 matrices, and you want the determinant of that of this expression. Determinant of this, which would be the product of the determinants. We know that determinant of U Hermitian, if I take the determinant of U Hermitian, then I get this to be equal to 1, because that is the determinant of the identity matrix. So, this can be written as the determinant of alpha sigma squared plus INR. Okay, one step away from a very useful and interesting result, and the determinant of alpha sigma squared plus INR can be visualized in the following way. It is the determinant of a diagonal matrix where the first entry is alpha sigma 1 squared plus 1, and then the second diagonal entry is alpha sigma 2 squared plus 1, all the way to alpha sigma L squared plus 1, where L corresponds to the rank of the matrix or the number of non-zero singular values, and that would be, and this would be given by product of I equal to 1 through L alpha sigma I squared plus 1. Okay. So, the summarizing the result, determinant of alpha H Hermitian plus INR, determinant of this expression can be written down as the product where the number of terms corresponds to the rank of the matrix H alpha sigma I squared plus 1. Okay. Now, the last of the properties, now look at the different expression, determinant of alpha instead of H Hermitian. Now, would like to look at H Hermitian times H. This has a dimensionality which is NT cross NT. So, this would be plus I NT. I would like you to try simplifying this along the same steps that we have done previously, and you can show that this is equal to product of I is equal to 1 through L alpha sigma I squared plus 1. Again the same result as in the previous case. So, in other words, we can write down the following result, that the determinant of alpha H Hermitian plus INT can be written as the determinant of alpha H Hermitian plus INR, right. That is what we have obtained from properties 5 and 6. And of course, we have gone through and shown the steps for doing this. This could have also been obtained from our knowledge of linear algebra, a result known as the Sylvester determinant theorem. The Sylvester determinant theorem states the following, states that if you have the expression determinant of I plus AB, if you have a expression determinant of I plus AB, and provided that the matrix operation AB and BA are defined, then we can write it down that this is equal to determinant of I plus BA. Okay, BA must be defined, and the dimensions of the identity matrix are commensurate with the dimensionality of AB and BA. So, given this form, then using the Sylvester determinant theorem, this is the result that is obtained, and this is identical to what we have observed in the previous result as well. So, this is a result, or these are the properties of the matrix H and the forms H Hermitian and H Hermitian times H. Okay, now why did we take so much effort to do this? For the following, and let us see what is the benefit of that. So, the log det capacity for a MIMO channel we can write down in the following form. The log det capacity that we have defined is C by B is equal to expected value of logarithm base 2 of determinant of sigma x squared by sigma n squared H Hermitian plus INR. Okay. So, the determinant is for this form, the logarithm is for the outer next bracket, and then the expected value. Now, this is a form where we are using H Hermitian. So, this is of the order NR cross NR. Now, this is a form that is very useful for us to work with when we have the receive antennas, dimensionality of the receive antennas as the limiting case, as the limiting case in terms of the rank. So, this will happen when NT is greater than or equal to NR, right, because in that case NR is the smaller dimension, and that is going to be the limiting case in terms of the number of non-zero singular values, and therefore H Hermitian, which is of the form NR cross NR, is a good expression for us to work with. So, let me call this as expression A, log det capacity expression A. Now, the alternate form of this can be given as C by B is equal to expected value of logarithm base 2 of the determinant of sigma x squared by sigma n squared h Hermitian times h plus I n t. Now, let me just draw the brackets. This is the determinant, this is the logarithm and the expected value. Okay. Now, in this case we are having the expression h Hermitian times h, which is of the dimensions nt cross nt, and this will be the limiting dimension when we have nt less than nr. In other words, when the number of receive antennas is greater than the number of transmit antennas, this would be the form, and we will call this as the form B of the log dead capacity. Now, are they different from each other? In essence, no, because we have just now shown that the determinant of this expression is the same as the determinant of this. So, basically when we look at the determinants using the Sylvester determinant theorem or the properties of the H matrix, we have already shown that these two are equivalent forms in terms of the value of the determinant. So, therefore, the capacity is still the same, but what it helps us is to understand and interpret the expressions in light of the dimensionality, and that is why we have two forms. One, when the case where NR is greater than the number of transmit antennas is greater than or equal to the number of receive antennas, and the second case is when the number of transmit antennas is less than the number of receive antennas, or the receive antennas being more than the number of transmit antennas. Now, the reason for this is for us to study two special cases, and these are very useful for us and interesting special cases. So, special case number 1, because they will reinforce what we have studied and also correlate with the earlier results that we have obtained. So, special cases, two special cases that we would like to look at. First one is diversity on receive. Now, this is the case where we were using diversity primarily to improve the robustness of the signal, where we use multiple receive antennas to pick up the transmitted signal, so that when we combine the received signals, we would then see that the effect of fading is mitigated through the multiple copies which are picking up independent fading. Okay. So, diversity on receive. Multiple receive antennas at the receiver. So, this would be the case where you would have number of transmit antennas equal to 1, number of receive antennas is greater than 1, typically 2, 3, 4, any numbers, and since we have the number of receive antennas greater than the number of transmit antennas, we would have to look at formula B. Formula in the log dead capacity, we will look at the version B, and the version B says that the capacity is given by expected value of logarithm base 2 of the determinant of sigma x squared by sigma n squared h Hermitian times h plus I n t, close all the brackets. That is the expression that we have. Now, since this is a receive diversity system, I would like you to help visualize what the channel matrix looks like. So, the channel matrix has a very interesting structure. It is the dimensions of HR are always NR cross NT. Since NT is 1, we have an NR cross 1 antenna in this particular case. So, in the general case H has got NR cross NT, in this particular case where there is only one transmit antenna and NR receive antennas, and the expression would be H11, the first index being the received the first one being the transmitted antenna, and the second index being the received antenna. So, basically what we have is H21, H31 all the way to HNR cross 1. So, basically there is one transmit antenna and NR receive antennas, and notice when we have Hij, these indices, it is from the jth transmit antenna to the ith receive antenna, and there is only one transmit antenna. So, therefore, we have only one column, for this. And when we do H Hermitian H, important for us to just write down that expression also. If you do H Hermitian H, what we will get is summation I equal to 1 to NR mod H I comma 1 modulo square. So, this would be the expression for H Hermitian H. Now, substituting this result in the expression, what we get is expected value of logarithm base 2 of the determinant. Now, this H Hermitian H is a scalar. So, this is a scalar. So, the expression inside INT, NT is 1, therefore, that is also. So, determinant of 1 plus sigma x squared by sigma n squared, I have interchanged the order, INT comes out as 1. This one becomes summation I equal to 1 through NR summation H of I comma 1 magnitude squared. Okay, logarithm of this and expected value. Okay. So, this is the expression that we have. Now, I would like you to pay following very careful attention for the following aspect of the discussion. Now, in the general case, the number of transmit antennas is NT, and if the variance of the signal transmitted in each of the antennas, so is sigma x squared. So, this is the signal variance at the transmitter. So, this is the number of antennas, and you can think of this as the power of the signal transmitted, transmitted per antenna, okay, and sigma n squared is the noise variance or the noise power, variance. Okay. So, given this, the total transmitted signal power is NT times sigma x squared, the total noise power in each antenna, sigma n squared. Now, this is the signal to noise ratio based on the total transmitted power that each of the receive antenna sees divided by the noise, and this we would like to represent in terms of the variable rho as the SNR variable. Okay. Now, in our case NT happens to be equal to 1. So, with NT equal to 1, then rho is equal to sigma x squared by sigma n squared. Okay. So, this parameter is nothing but rho, and it very important for us to be able to characterize this expression. So, we will write it in the following form. So, this is equal to expected value of logarithm base 2 of the determinant of a very important form, and the important form comes out to be 1 plus NR times rho times 1 by NR summation I equal to 1 through NR mod I comma 1 whole square, and the put in the brackets, this is the expression for the determinant, the expression for the logarithm and then the expected value outside. Okay. So, what we have done is basically written this expression in terms of rho, and we have also introduced the NR and 1 by NR, and it is for a very specific purpose, because NR times rho, the SNR of one antenna multiplied by NR, this tells me that this is the array gain. Array gain tells you that when I have NR receive antennas, it is like boosting my effective SNR by a factor of n. By the same token, 1 by NR times this summation is precisely what we would refer to as diversity gain. If you remember our earlier discussions, this is what we refer to as the diversity gain. Now, the diversity gain comes in because not because it shifts the energy of the signal. On average, this quantity is equal to 1, but at any given time, because these signal levels are fluctuating, what you are getting is the benefit of the stronger signals when there is fading is present. So, that is the diversity gain. So, we are able to see that the expression that we get for the log dead capacity of a MIMO channel on receive directly correlates to the expression that we have obtained when we were using receive diversity, because when we were using receive diversity, what was it? It was basically we can leave out this is a scalar 1 plus. So, the determinant really does not make a difference, we can leave out this. So, this is nothing but expected value of logarithm base 2 of 1 plus SNR on received diversity, where SNR is given by the expression for a received diversity system, where you have array gain plus diversity gain, and this is exactly what we had obtained earlier, and our expressions now are matching the expressions that we had obtained previously, where the SNR is the effective SNR in the context of received diversity. Okay. So, diversity on receive completely explained in terms of the log dead capacity and shown that it matches the expression that we have derived earlier. Now, we would like to develop this a little bit more for the second special case. The second special case is transmit diversity. So, special case number 2, and this will be for transmit diversity. Now, as you know, transmit diversity is a case where we have multiple transmitters, but possibly only one receiver. So, NT is greater than 1, NR equal to 1, we will take that particular case. So, in that case, the dimensionality of H is 1 cross NT, and the so based on this structure, we will use the formula A for the log dead capacity, because that is the one that corresponds to the case when the number of transmit antennas is greater than the number of receive antennas. So, under this formula, we get C by B equal to expected value of logarithm base 2 of sigma x squared by sigma n squared H Hermitian plus INR. Okay. So, this is the logarithm. I have forgotten to write the determinant. Okay, I need to shift this. So, it is logarithm base 2 of the determinant of the expressions, and let me just write it with different colors. Determinant of this form, logarithm of this, and this is the form that we have of the expression B. Now, I would like to write down what H looks like. H is one receive antenna, multiple transmit antennas. So, it looks like H11, first transmit antenna to the first receive antenna, H12, second transmit antenna to the first receive antenna, all the way to H1 comma NT, from transmit antenna NT to the first receive antenna. And if we now do H Hermitian, this comes out to be equal to summation I equal to 1 through NT mod H1 comma I mod squared. So, H Hermitian takes the following form. So, using this expressions in here, we now obtain that this is equal to expected value of logarithm base 2 of the determinant of the following expression, where it is 1 plus sigma x squared by sigma n squared. Again, I have used the expression for nr to come into the first place, sigma x squared by sigma n squared. This will be equal to summation I equal to 1 through NT mod H1 comma I magnitude squared. Now, notice that this is also a scalar. Okay. So, then we can simplify this expression. This is determinant, this is the logarithm, and then outer is the expected value. And we can show that the because it is a scalar, the determinant does not play a role. So, this can be written in the following form. This is expected value of logarithm base 2 of 1 plus. Notice that if I were to now wanting to write the sigma x squared by sigma n squared in the form of rho, then we know that rho is equal to NT times sigma x squared by sigma n squared. So, sigma x squared by sigma n squared can be written as rho divided by NT, okay, rho divided by NT. So, this can be now written as 1 plus rho 1 by NT times summation I equal to 1 through NT mod H1 comma I magnitude squared. So, close bracket, and then you get the expectation. Now, very important result that if you recall, when we talked about transmit diversity, we said that transmit diversity systems will not have array gain. Notice that the SNR here is no array gain, there is no array gain, but transmit diversity systems can achieve the diversity gain. So, if you notice that this expression allows or shows that there is a provision for the diversity gain, no array gain, but diversity gain is present. So, this is also consistent with our understanding and derivation of the results that we had obtained for the case when we have only transmit diversity. So, the good thing is whatever we have derived as the log dead capacity can be used to look at two special cases, one with received diversity, the other one with transmit diversity, and in both cases we have shown that the results are completely consistent with what we had derived earlier. Okay. So, to summarize, what we have done is, in the case of a MIMO channel, let me go back to the first drawing. We have the following expression y is equal to hx plus n. When we know the channel at the transmitter, we have been able to do the parallel decomposition. When we have the case where we do not have knowledge of the channel at the transmitter, then we have estimated the ergodic capacity. We have obtained two versions of the expression, one when the number of transmit antennas exceeds the number of receive antennas. This is a special case when you have just transmit diversity, when NR is equal to 1 and you have multiple transmit antennas. On the other hand, there is an alternate version which gives us exactly the same numerical value, but the expression is more consistent with our intuition for the case where NT is less than NR. This is the case when you have received diversity, and we have shown that this also is completely consistent with the case where you do maximal ratio combining type of expressions. So, the two special cases, and then finally that we now have this final expression. So, with this we would now like to conclude our discussion in terms of the capacity of the MIMO channels. Now, one of the important elements is how do we combine coding and multiple antennas, and that is a very important element in our discussion. So, let me introduce the final part of this particular section, where we would like to look at MIMO transmission and coding. MIMO transmission and coding. And it is a very important result, important section for us, and definitely something that you should pay close attention to. So, let us look at some of the MIMO transmission plus coding. Let us take a couple of simple examples, but before that let me introduce the notation. So, if you have the following scenario, I have NT transmit antennas, that is transmit antenna number 1, transmit antenna number 1. Similarly, all the way to transmit number antenna number NT, transmit antenna number NT. And let us assume that we are having only one receive antenna, okay, just for simplification of the notation. So, the first receive antenna, and this will tell us that the channels, now I can write it in terms of just one index. This is channel H1, and the each of these antennas will give me a channel, and this is channel HNT. Okay. Now, if I were to transmit the different sets of n inputs. So, basically input number 1, input 1, this would be input NT for each of the time instances. So, in other words, we are going to write down a matrix where I indicate what I have transmitted on antenna 1, what I have transmitted on antenna 2, all the way to antenna NT, and the x axis will be the time index. This is time n equal to 1, n equal to 2, and so on. So, this is x of the signal transmitted at from antenna 1 at time instant 1, x from antenna 1 at time instant number 2, and if there are n time instances, n is equal to uppercase N, this will be from antenna 1 up to time instant n. Similarly, from antenna 2 it will be x2 comma 1, x2 comma 2, all the way to x2 comma n, and finally when we look at the nt comma 1, nt comma 2, all the way to x of nt comma n. Okay, so, this is our the matrix which collects all the transmitted signals. So, this entire vector is transmitted at time instant number 1, this entire vector transmitted at time instant 1, okay, and the next vector transmitted at time instant 2, at time instant 2, and so on and so forth up to n block. So, we now have this matrix which is NT cross n. This corresponds to the number of time intervals, and we can also refer to it as the block length of the block. So, NT antennas and block length equal to n. So, this matrix that we transmit, this matrix that we transmit is what we refer to as the code word, that we are transmitting. Okay. So, the code word or the information that is being transmitted. Now, how is this matrix going to be generated? That is a very key element, and that is what is going to give us the different cases that we are going to be looking at. So, at the receiver, what we can write down in the form that we are interested in is the input output relationship, which we can then write down in the following manner. So, let us see how to look at some of the cases that we have already studied. So, first let us look at the Alamuti case. Alamuti case is one where we transmit, this matrix is a 2 by 2 matrix. We transmit symbol S1 from antenna 1, and in the time instant 2 we transmit S2, and so this is antenna 1 and this is antenna 2, and we transmit minus S2 conjugate and S1 conjugate, and then this repeats. So, this is the code word or the code matrix that is transmitted. So, if we were to describe this, the Alamuti case is a case where we have NT equal to 2, and in 2 time instances n equal to 2, number of symbols transmitted is equal to 2, number of transmit. Okay. So, 2 transmit antennas, 2 time instances, 2 distinct symbols that are transmitted. So, therefore, the rate, which is the number of symbols transmitted by the number of time instances, is equal to 1. So, the Alamuti case is a case where you have a rate 1 code, where you are transmitting 2 symbols over 2 time instances, and you are able to achieve the second order diversity that we have shown is present in the case of an Alamuti system. Now, a similar case, but a simpler one. When we do repetition code, that means first we transmit a symbol on antenna 1, nothing on antenna 2, and we then in the next instant of time we transmit the same symbol from antenna 2 and nothing on antenna 1. So, in this case the matrix would be S1 and nothing on antenna 2 at time instant 2. So, this is antenna 1's transmission, this is antenna 2's transmission, time instant number 1, nothing on antenna 2, and then second time instant nothing on antenna 1 and S1 on antenna 2. So, basically you have done a repetition, transmission on 1 and transmission on antenna 2. So, in this case we have number of transmit antennas equal to 2, number of time instances or block length equal to 2, number of symbols transmitted is equal to 1. So, this is not as efficient as the Alamuti scheme, because this one achieves only a rate of 1/2, but of course has the same diversity, second order diversity. So, in a nutshell, what we are trying to do is we would like to have the rate as high as possible and at the same time achieve good diversity methods. So, now what we would like to do is very quickly and very briefly introduce the concept of what is one of the most popular techniques called the blast techniques. So, the blast architectures, Bell Labs layered space-time architectures. Now, these were the architectures that were so this is what stands for BLAST. This was introduced in 1996 by researchers at Bell Labs, several of them. One of the pioneering papers was by Foschini in 1996. Now, here are some of the basic assumptions and the structure of a BLAST method. So, we have input data, let us assume that this is binary data, and we have 4 antennas. So, we are going to do a demultiplexing by a factor of 4, 1:4 demultiplexing. So, we will get 4 parallel branches coming out of the demultiplexer, okay, 1:4 demultiplexer. So, this is a demux. Now, each of these are going to be processed, each of these substreams is going to be processed by an combination of encoding and modulation. So, this is encoding modulation block number 1, and then we have encoding modulation block number 2, block number 3 and block number 4. Notice we have already segregated the streams, and each of these streams are we do modulation encoding independent of the others, and typically we can use encoding or encoding methods such as convolutional codes. So, it is conventional coding as example will be convolutional codes or block codes in any of the standard codes that we are familiar with. So, we are using standard codes, and we have separated the data into multiple streams, and we will transmit through the different antennas. So, this is the case where we have designed the structure for 4 antennas, 1:4, and we will see that there is a very important block in the middle which is useful for us in as part of the Bell Labs structure. So, this is the arrangement that we have, transmit antennas, and this is a form of something that does cyclic association. Basically, it is like a switch that keeps shifting the input signals from one antenna to the other. So, this is called cyclic association. Okay, so, it is like a circular switch, and we will show what that actually does when we do the transmission. So, basically one of the simple forms of the MIMO transmission is the blast technique, which was first introduced in 1996, showed that we could achieve very high spectral efficiencies. In fact, it was even shown that you can achieve as high as 40 bits per second per hertz. Okay, so, very high spectral efficiencies using this structure. Now, what we would like to do is pick it up from here and basically describe what is the encoding process, what is this cyclic association, and how does it benefit us in terms of achieving the performance of the system in terms of getting the diversity benefit, but also getting increased data rates, which is what will achieve for us the high spectral efficiency that we are seeing here. Okay. So, tomorrow's lecture will be a brief introduction or brief introduction to the topic of the space-time codes, and just a mention of what are some of the elegant methods that are used and the powerful results that we can achieve with the space-time codes, which are built on the MIMO framework that we have been studying. So, that will conclude our discussion on MIMO techniques and then move us into the next topic, which will be OFDM techniques. Thank you.